Um, okay, hello. Hello, could you hear? Yeah. Hey, hello. Yeah, I think it's starting recording right now, so we can starting our biweekly development meeting right now. Okay, and welcome everyone. And let me give you a brief introduction of today's meeting.
So yeah, let me share my screen. Yeah, so today we have two things to discuss. The first thing is like collaboration with the OpenRLHF team to discuss what kind of interface we can improve to make the integration with RLHF workflow better. So later, Xiao and the RLHF team, OpenRLHF team will have some discussion and list some specific requirements. And then Hai will talk about some proposal on how to make quantization better in the current SGLang. So he has extensive experience building this standard and interface for quantization. So he will present some ideas. If that goes well, we will probably implement his proposal as the main quantization strategy in the SGLang. Okay, yeah. Then Chaoyang, could you lead the RLHF discussion?
Oh, well, okay. Hello, yeah. I think the discussion we're starting from Ziling, right? You're online, and could you hear?
Yeah, I can.
Yeah. Hello. Okay. You can probably share your screen and let's start. Right.
I don't really have anything to share on my screen, but I can like make a simple description of what we are trying to do. So first, I'm Zilin Zhu from a member of the OpenRHF team, and we're trying to provide the best training experience of RHF like in the open source community and maybe for the researchers. And currently, we are trying to use SGLang as a better alternatives to generate samples and maybe like serve reward models in the typical on-policy RLHF training.
Hello. Sorry to interrupt you. Could you please maybe you can share your paper or share your GitHub repo to give us illustration of what you are doing?
Yeah, I just a moment.
Yeah. You can send the link to the message. Okay.
Yeah. Just a moment.
Yeah. Thanks.
Oh, sorry. Sorry, wait for a moment. I don't know why the internet connection is kind of bad here. Right.
Okay. Nothing. Byron, could you help us share that, or could anyone do that?
What?
Yeah.
What did you say?
Maybe could you help us share your screen and presenting the OpenRLHF GitHub repo?
Me?
Yeah, it's on the chat channel.
Okay.
Yeah.
Desktop.
Share my screen.
Yeah, and open that GitHub link. Yeah. Yeah. Okay. Yeah.
Yeah,
And
this one.
let's make
Yeah, thank you so much.
Yeah,
thank you.
Yeah, maybe you can help us go through some like features and some like issues you met.
Yeah.
Are you trying to like go through the whole training process or just trying to see where we will use the SGLang?
Maybe 5 minutes on the high level like architecture, and then the remaining part we can talk about how you are doing integration with inference engine.
Yeah, okay. So maybe I will try to like share okay. like can I try to share the screen because it's hard to like tell him to like click on certain links. Or you
Do you not
can
have the access? Let me see. You should have the access. I'll try again. Try again now. There is a share button you can click.
uh-huh. Yeah, can you see my screen at the moment? No?
No.
Uh,
Can
oh,
you see the share button?
I may have to like quit, like re-enter Zoom because I haven't.
Yeah. Yeah. That's pretty cool. Yeah. Okay. Mm, just wait for a second. I think today we are flexible about our meeting time, so maybe we can somehow like extend it for 10 minutes and somehow we can have more discussion right now. Okay, we see. Hello.
Again.
Hey, hello.
Hey, this one.
Oh yeah, good. Yeah,
Yeah,
cool.
like
Yeah.
Like this
Yeah,
is
thanks. We can see your screen.
Great.
Yeah.
So are you seeing? Can you see the like the GitHub of OpenRLHF? Because I have two screen right now. I'm not sure which one I'm
Yeah,
actually.
yeah.
Yeah.
Yeah, right.
Yeah, that's great. So, like OpenRLHF is just, oh my, it's so gleeky. So OpenRLHF is like a repo trying to implement a lot of RL algorithms like DPO, like KTOs, and all those things. And especially, it is especially good at training PPO, which is like the mainstream on policy like training. Uh, Algorithms that we are using right now. So this is how we train the model, and we are using Ray to uh, like scheduling a lot of different components of the training, like of the PPO training process. And if you're familiar with PPO, there will be like four kinds of models in the PPO process: an actor, and critics, and reference model, so that we can calculate like the KL divergence between the current policy and the origin policy, and also a reward model, so that we can know like the how good the samples are. So if like you want to read through the OpenRLHF code, which is like quite simple, you can go like use the train PPO rate.py and like an entry point, and you can see how we like just set up the actor model, set up the ref model, and then the critic, and then reference model. And here we will like currently using VLM, and here's how we like create the VLM so that the VLM will load the weights from of the actor, and then like generate the samples like during the train time. Like that's the entry point. And for the main parts where we need to use the VLM, you could go to see the let me see the parts of how we are going to generate a rollout, or actually the you could think of the training data of the PPO. Oh, my VPN is so slow. I don't know what's happening.
Easy.
Uh, this one, like Experience Maker, which is you can see like an online data loader, which is trying to generate data from the current model, and you can just get like make experience here. So we'll first make experience. I will then go into the like the make experience method to tell you what it's doing, and then after like generate some samples, we'll try to calculate the rewards, the like the advantage and returns, which are like specific things of the PPO. So for VLLM or like and maybe SGLang in the future, this. Yeah, here. it's quite simple. We just pass a list of prompts and we ask like the serving like the servers to generate results of the prompts, and then we pass the results like into the reference model to calculate like the origin like log props, and then we pass.
三个音，我他妈不知道听谁的。
Oh, sorry. Is there any like anyway?
I think it's good with us. Okay, you can go ahead. Thanks.
Yeah, and then we will pass the like the outputs to the critics to get the value, and then we'll also like pass the results to the reference model, and so that we can get the rating of them, and then we will save them into basically a list and pass it out, and then calculate advantage and stuff. So that's basically the like the main procedure of how we were going to generate the online data for PPO training. And for the SGLang part, we're hoping like to do two things with SGLang. One is like exactly what like the generate VLM is doing. It's just we will pass prompts and it should returns a lot of responses like with regard to the prompts. And the second thing is we hope that like you can see there's a reward model, and we have like you can serve reward model as a remote URL so that you don't need to host the reward model in the cluster. But on the other hand, you can like serve reward model within the Ray cluster. But right now, because no matter like VLM or SGLang, there's no really good way to serve an like arbitrary reward model. So we have to use the reward model as an Hugging Face model, which is like inefficient. And so that's one like feature request we hope with the we hope that we can work with SGLang is that most reward model are just causal models within another linear layer. So sorry if I didn't express myself like clearly. You can just interrupt me in that question.
Yeah,
Okay.
it's
Because
good.
I haven't speak English for a really long time, so I'm not sure I'm like really expressing the correct thing. Okay. So
Okay.
back to the feature request. So one thing is to like we hope we can use like an inference engine to really host the reward model in a like much more efficient way. And also we don't hope that, for example, if we want to train a like a llama model, we don't want to write a llama reward model inside SGLang, because maybe like tomorrow I will change to a QN model and then we have to write the whole things again, and that doesn't seem like a correct way to do so. So we hope there will be a generic way so that when we want to serving a reward model, we can just like we can just choose a causal model, and we may add certain kinds of like linear head or maybe multilinear head to it, and then we can just simply host it with SGLang, and that will be like easy to use, and that will be much more efficient. Like that's one part of the feature request. And the second part is like more like RLHF related, is that because as I said, we are generating data online, which means like we create some data, we don't train the model, and the model changed, we need to update the serving engine so that we can generate new data with the newly updated weights. And therefore we need to have certain ways to communicate between the training process and the serving process. Most people just call it like we do a weight synchronization, and currently we are doing that in a quite hacky way. Let me see. It should be in. Oh, not this folder, which I Let me search for that. It should be like it's just so this one. So currently, in order to update all the weights, we add a wrapper to the VLM workers, so that and create a nickel or maybe glue process group between all the VLM workers and the one of the process in the training one of the GPUs within the training process, and then whenever we just finish a round of training, we will do a broadcast, and the training process will just broadcast the weight to all the worker process, and then the worker process get the weight and can update it directly. That's basically what we're doing right now with VLM, and like it is not a native supported feature by VLM, so we trying to hack that by derive the origin worker class and add some function to it, which is like kind of burdensome. And whenever VLM has some changes, we have to adapt it like correspondingly, which is really, really annoying. And so we think that if no matter if SGLang hoping to provide a really good experience to the RLHF training process, it would be really nice that SGLang can have a more like native support for the weight synchronization. And for the weight synchronization, there can be a really like simple implementation that we just add a function in the Python LM engine, like update weight, so that we can from the training process can send all the way to the master process of the SGLang cluster, and the master process can then scatter the weights into the tensor parallel workers. That's like one naive way to implement. So, and but in that way, we have to like first move the weights onto from GPU to CPU and send to the CPU master. And from the CPU master, we then like somehow send to the worker, and because the worker weights are on GPU, and then we copy it back to GPU. That will be kind of inefficient. So if we trying to make the performance of the weight synchronization in SGLang good enough, we may need to have a way to expose the workers to the outside, so that we can like directly send things like into the workers and update the workers' weight. That's
啊，你
basically
说什么？换一个短一点的。
So yeah. Anyway, that's basically the two things we hope that we can work together. Like first thing is like going back. First things is maybe have a more generic way of serving reward model, and second thing is maybe have a like more like intuitive way and more like efficient way to do weight synchronizations between the training process and inference process. Yeah, that's basically what we are hoping to do.
Okay, pretty clear. So, are there any comments, or would anyone want to ask more about your own RHF process that need the support from our inference engine?
Yeah, so yeah, I think this is very good. Okay, so yeah, like the code work through is very helpful, and I think now I understand much better like what we should do. Yeah, so I look at these two APIs. Yeah, I think yeah, these are very like I think these two APIs are very good. Like we can make it a standard in SGLang and always maintain that. Yeah, so I guess for WaveSync, probably yeah, we can just maintain like a stable version of these two APIs. Yeah, I think the current signatures of these APIs are very good and correct. We can support them. And for the reward model, probably that part, yeah, can you show us how the current reward model is implemented?
Sure. Just a moment. I think it's in the model. Oh no. Just a moment. Just search with the GitHub. Just here. Oh, this one. Yeah. We just add a linear after the loaded base LLM, and we can name it whatever we need. Maybe it's called a value or call it value head or call it score. And then in the forward, just get output from the base model and get the last hidden states and send the hidden states into this linear, and that's all we're doing. And then this model will be initialized with deep speed, maybe deep speed 0.3, and just treat it as a Hugging Face model with deep speed, and we will send the data into batches, something like that. I'm not sure if this is enough.
Yeah, this is helpful. Okay, yeah, I think I know it's much better. And I also want to know, like, because you now have so many components, and when you run like a training loop, will they all be active at the same time, or every time there will be some GPU idle?
Currently, they won't be running all at the same time, but we can do there are four components. Actor, critics, those two will be trained, and they will be training simultaneously. And then there will be a reference model, just trying to involving creating data, and that basically cannot be activated during the training process because we need the new weight so that to get the new samples. And there's also a reward model, and reward model is basically only activated during the the data generation phase. And also there's one thing that we didn't share the GPUs between the training process and the serving process. For example, there may be 8 GPUs doing serving and 8 GPUs doing training, and but maybe if we want to make the GPU used more efficiently, we should put them on the same 8 GPU. And when we are doing inference, we can just maybe move those weights back to the GPU, and after use that, we just move it back to CPU. But for at the moment, we just separate to make the whole structure cleaner. I wonder if
I
this.
see. So basically,
Mhm.
when the training is running, the inference engine are idle.
Yeah.
Okay, and now like what's the ratio between them? Like how do you choose how many training GPUs and how many inference GPUs?
It's at the moment we only support as many GPUs as the training process. Sorry, I mean we only support as the inference servers as uh are less than the number of training process, but that can be changed. Like I wonder if let me just show the code just a moment.
Yeah, I see. Yeah, like this is very interesting. Like how do you decide the ratio between them?
Uh, Currently it's just a very menu design. Sorry, not this one. I think it should be actor. Just a moment. I just go to look it up in the VS Code so that it will be easier to look. Let's just use the VS Code. Yeah. Yeah. So this is the generate VLM function. If you I just mentioned about when you want to create data, you just code generate VLM to create data. And right now there will be many VLM engines, and we'll just use the rank of the training process and then select one from the origin VM engines. So with the current implementation, we can only have fewer VLM engines than the training process, but that can be changed, and that's also something we are trying to change.
I see, makes sense. Yeah, and because Byron is, yeah, I guess probably like a better load balancer here can also help. For
Yeah,
example, Byron is
actually.
working on a advanced load balancer. So like in the future, probably you can plug in it here, and then that does better load balancing for you.
Exactly, and also currently the current implementation we to make the code easier to read, we have sorry this one we have like scheduled the prompts into batches previously, but in fact we can just send all the prompts to the serving cluster, so that the serving cluster itself can do the load balancing and maybe just find a better way to find a more efficient way to generate the samples. And that's also one thing we are discussing about.
I see. Yeah, makes sense. And when you generate because now you generate a batch like batch by batch, right? So
Yeah.
do you notice like any delay or struggler in the whole process? For example, you have many inference engines and one may run much slower than others because, for example, the generation is long. Did you also notice these problems?
Currently not much because the prompt like a typical prompt in the training process is just a math problem, and so most math problems are of the similar length, and the response are like in around like 100 to 300 tokens. So there won't be like a question with a really long response and uh, like one question with just like 2 words response. But I can imagine that happens, and especially when like people are training O1 like models, that will happen because O1 will have like really long COT and it will create the variance of the response length.
Yeah, makes sense. Yeah, so I think it will also be good to uh like get some like observability tools in OpenRLHF, like monitor all the GPU usage and like all the like idle time. Like if you have such a like visualization, we can quickly identify some bottlenecks.
Yeah. We should add that. Yeah.
Okay.
Mhm.
Yeah, I think this is very good. And I think Chen Yang will lead the integration support. So basically, reward model and wait update. Okay. Yeah, thanks. This is very helpful.
Yeah. Thank you so much. Okay. So I will stop sharing my screen. Okay. Okay.
Yeah, great. Yeah, Chen Yang is muted. He tries to say something. Hey, okay. Hey, Chen Yang, you can try to unmute.
All right. Hey, hello. Yeah, could anyone hear? Yeah. So, thanks for your presentation. Yeah, as we have limited time, do anyone here have your own usage for your RHF? If you need any help or something similar to what Ziling have said, could you directly describe it? Or if not, we will move to the second part. Hello. Okay, so I think there's no one on the city right now. Okay, but we will have a channel to discuss this kind of integration of OpenRLHF. So maybe you can, if you have this kind of thing, you can go to our general channel in our Slack and ask it. So we're gonna go to the second part, right? Okay. Hey, so
Hey, hello. Hey, my
hello,
name is Hai.
hello, yeah,
Hello, good.
yeah, hello, cool.
Let me share my screen. Hello everyone. Just share save bandwidth and disable the video. Okay.
We cannot see your screen.
Yeah, I'm doing that right now. So I didn't use the Zoom too much. Sorry for that. I have two screen. Let me see if I share the right one. Oh, it says need to season setting. Sorry for that. Some configuration security reasons.
Yeah, it's easy. You can
Yeah.
relaunch the Zoom and enter it.
Give me a second. I didn't use Zoom too much, so Share screen. It's not shared, right?
We can't see it.
Okay, let me do it again. Really bad. Okay. Can I send to Liamin?
I think I do that, or you can. If that's
I
a link,
think
you
you can just
directly
quit
post
and
it.
rejoin.
Oh, okay.
Yeah.
This is bizarre. So this Zoom thing is not easy to use.
Yeah, if you have a link, you can share us to through the chat.
Yeah, let me join again.
Okay. Yeah. Thanks. Okay. Hello.
Sorry, what was?
Right?
Hello.
Okay.
Yeah.
Can you?
Hi. Yeah. Hi. I think you can unmute and share the screen now. Can you try? Hello.
Oh yeah, I'm muted. I'm now share my screen. Okay. Let me send my document to Liamin or someone, because I think I didn't use very often on Mac of these tools. Okay.
Or you can just send it to me. Maybe you can
Yeah.
select me.
Yeah, it's like you guys. So you help me to share. Oh, I sent to Liamin. I'm sorry. Liamin, I can send you again. Let me send one more time. Let me send you now. Yeah, sorry.
To who?
It's very bad.
To Liamin.
Send you. Let me send it to you as
Me?
well. Yeah, I think Liamin already received it, but I'll send you right now. You should be receiving
Okay.
in one minute.
Liamin also send it to me. Okay.
Yeah. And maybe you can share. I just talk. Sorry for that.
Okay, 1 second.
I have Keen, I have Google, I mean, too many different security gate wasn't open on my Mac. It's kind of hard to find it.
Right.
You got it, right?
Yeah.
Oh yeah, I see the file. Yeah. Yeah, maybe you can do full screen. I think you're shared the wrong.
Right.
Okay,
Yeah.
Yeah,
That's
cool.
good. Hey, thank you. Let's from beginning. Thanks for the patient. I lost 5 minutes probably. Should do better next time. This just to give the title wasn't really catching because I put MI300 on top, but really it is not only to MI300, right? It is also to OCP, Open Compute Platform, proposed leading by Meta. And OCP APA formatting is identical as NVIDIA's. Next page, please. Yeah. So before people may ask why there's such difference. Why AMD's APA kernel 300 is different than OCP? It's all come from the history. We started our hardware design probably the first coding three years back. At that time, NVIDIA has not done any product onto the market, so people have different design. Our design is very in line with Graph Core, very well known, I think, probably in hardware business at Cambridge, UK. So when NVIDIA released, we see there's a little difference. Again, it's also because in this newer formatting machine learning data, there's no IEEE standard yet. IEEE is moving slow. It's very official stuff. So even today, IEEE APA standard is not there. Right. So okay. So the focus of the talk it's really to deal with this chaos, how to interrupt, how to consider different formatting, and how to move forward. Okay, so let me go on this page, right? So this just not to only deal with story type. When we talk about story type, for example, AP Inter 4 or something, you almost have no hardware unless you write your own circuit in APJ. There's no much available GPU do Inter 4 matrix multiplication, Inter 4 quantization, whatever software you use today is just for storage, right? So you have weight, quantize Inter 4, you save to the HBM, I mean memory of GPU, then you load back, then you upscale to either AP16 or APA to do computation. But this talk really trying to differentiate the primary data type in newer ML capable hardware. When I say primary data type, it means flow 32, flow number, flow 16, half flow number, and next one is APA. Right, Inter A is there, but I will talk about later why Inter A is less talked about in new hardware direction. And then we're not talking about Inter 4 because Inter 4 is just storage on. This first bullet is about. We're focused more on the hardware enabled formatting and how to make use of it. It's more like AP16 introduced like 5 or 6 years back. NVIDIA do Apex, right? And later on Torch AMP, automatic mixed precision trading by using AP16, not too long ago. It's just 4 or 5 years ago. And also this is not about just weight only. Weight only, if you wait most times stationary after train for inference, you can do whatever you want pre the runtime. You can pre-quantize, shrink in the memory, you just load in, extract, then do computation at higher precision, whatever your hardware supports. It's not just about that, right? And so the focus of this is not just APA, but it starts from APA. Right, this APA we talk about dedicated to E4 M3 is only for inference. Used primarily, this is start from 2019, a new paper from Xiao. It's a colleague of Lianming, fortunately, yeah, at XAI today. And he had a paper on hybrid 30.8, right? And that's where we start from. Then we move to the newer data type later. So here we talk about, I'm saying Inter-A, we do have hardware supporting the multiplication, but we consider it's inferior to APA. Inter-A have longer history, easier to do, but for the numeric stuff, it's really not better than APA. But anyway, if you think about Inter-A has same hardware performance as APA. It's amazing. APA is floating point ABs. Inter-A is integer. It's linear integer ABs. The computation speed is same, but it does not have the advantage of APA. APA has more dynamic range. The range is bigger, and the dots on the axis is not linear, right? You have denser dots near to zero. You have a more sparsely gap for the number far away from zero. This is a floating number in computer science fundamental stuff, which we know that. And now we talk about scale or not. Scale, I'm talking about really adapting to high precision number to APA or even lower precision. There are many cases people say, oh, we don't need a scale. Okay, without scale, it's fine. You do linear, scale is a linear transformation. But if you don't, it's very hard, right? So let's say people say I have AP16. AP16 is 1, 5, 1, 5, 10. 1 is sine bits, 5 is exponent, 10 it is mantissa. I can do this directly to E5M2. APA, one of the APA format is 1 sine, 5 sine exponent, and 2 bits mantissa. I just chop off the remaining 8 bits, these significant 8 bits, and round it to the top 2. And people said that would work, but I would say that might not work in most cases. Because if you look at the floating number system, you have sub-norm ranges, which is also called D-norm ranges, which is really small numbers, high density near to zero. So if you do AP16 high precision number, if your number in your tensor or whatever is all small number, this small number is fall below the floor of APA, then you basically run everything to zero. You can't observe it's just too small. So I'm saying even 1510 to 152, the better you still do scaling. I'm saying scale always, but how to scale? It's like sprint. If you higher precision number, the range is bigger than lower precision number APA or even lower, you compress, right? You compress. If you high precision number or small, in very small, tiny, small range, then you pull the sprint to make it occupy the full low precision numerical domain, right? It's like just it's a compressor expand. That's the state of art. It's not the state of art from research, but state of art of industrial application. We do that right now. So we change it. We scale. We send the scale the number to hardware do multiplication. But as you know, since you do that, your result of hardware circuit of multiplication is not like a regional multiplication done by hardware on higher precision, right? So you need to reverse back. You need once you get in the circuit and computed the result of the multiplication, you need to do inverse scale back to the high precision domain. That's why I say reverse to higher precision. So now the other anomaly is dynamic scale or static scale. We know scale to a high precision number to lower precision number. This takes time, takes some effort. But if you scale as a whole of a big tensor, that by itself very expensive. But on the other side, if you scale to just a small chunk of data, it's pretty fast. So I'll touch later on the MXFP from OCP. It's just a block of 32 or multiple of 32. You can say 2 or 4 of 32. So basically, you're dealing with consecutive numbers, 32 or 64 numbers. You do scale based on that. And that can be done relatively fast. So there's no single conclusion say you should never do dynamic scaling or you should always do dynamic scaling. But for the use case perspective, dynamic scaling guarantees your accuracy better because you're not worried about out of distribution because everything you see, you just recompute scaling factor on. So it's widely used for training or for loss sensitive applications. Now back to people why. Then why you do static scaling? Again, let's state the bar for what we today use for most cases, not every cases. For example, for large language model, we use static scaling for tensor. This tensor can be big, can be per, for example, per head or per tensor parallel partition, but we do per tensor level, and we found it still very practically useful. So that, but it's very fast, right? Because for scanning, static scanning, you compute the scanning factor upfront, not on the real traffic you encounter, system sees. How you get it? You use the quantization. You use with calibration. Like you send a bunch of testing data samples before real deployment. It can be a lot, it can be a few, can be full data set you have. Just go through the calibration. You compute the based on that. You do the scanning factor and you deploy this scanning factor to the runtime for the inference. That's scanning factor static how it works. Still today is used for inference in a lot of cases. The bottom one is just to introduce some API data. Primarily, I just highlighted two buckets. There's the third one is from Google chips, but I just ignore it. I'm gonna talk about the GPU. The green one, it is OCP per se, also identified as NVIDIA. The orange one, it is one AMD has it as a MI300. Yeah, better news. From 325, our next chip, end of this year or early next year, we'll also have a green type. So basically, AMD next chip, we're supporting both types. Again, this initial discrepancy is only caused by the history. It's not by purpose. So moving forward, we're trying to follow the OCP format. Next page, please. Yeah, this is just a very simple show what it's about when we say E4 M3 or E5 M2. There's always sign bits. The first one left is a signal sign, right? Positive, like negative 0, positive 1 minus, and the 4 bits exponent. Then it's all like the purple one. It is the right one. It is Mantissa. This one is exactly the same like floating point 16, flow point 32. It's just different numbers. So 8 bits, right? So for the background, I had given this paper reference to Xiao's paper. That's where the first paper mentioned about the hybrid floating point, forwarding using the top one, backwards gradient using the bottom one, and that paper has a great mention there, and empirically shows best performance for training and inference. And here I'm saying for the E5153, it used mostly for forwarding parts. It used for weight and activation if hardware do use these two doing MATMOL. The E52 is mostly used for gradient. And for inference, like for SGLang, VRM, we probably shouldn't worry about it. Yeah. I had like our instruction set at the bottom. It shows all the instructions. The one I just list out. I'm saying for the in the middle, I give you full instruction examples. So first one, you say BF8, BF we already mentioned E5M2. So both operands in E5M2, which we don't worry about for inference. The second row, it is the first operand, matrix A is E5M2, matrix B is E4M3. No, we don't use for inference, right? Same for the third one. The fourth one is mostly used for the inference done by this hardware multiplication. The both operands, both matrices E5 and M3. So yeah, that's just an example. Next page, please. Yeah, here a little bit more detail. And this will leading to next page, how we design and solve that interrupt problem. And you see OCP NVIDIA side, and then you see right side our 300X side. I'll give very quick. Not many people probably shouldn't or be interested in this detail. Right? You look at this number. The most left side is bytecode. right? It's 8 bits bytecode. And you see for the same pattern of bytecode, the numbers from different chip, the means different. And worse, there are even special code. For example, the last one, the first red arrow from top, you see on the left side, the NVIDIA side, it means not a number. On our side, it means 240, right? So the next red arrow on NVIDIA side means -0, on our side means infinity or not a number, right? So then how to solve this? Let's do next page, please. Yeah, so interesting is for inference is quite, we can play quite trick there. So for inference, we had a good assumption, right? So the pre-trained network weight is not supposed to have not a number or infinity, right? You're doing inference, the weight should be already in good shape. And so what I mean is if you look at the two, the red, the green, I drew two green rectangle there. I dedicatedly leave 240 on right side out. So basically, if you look at the right column on MD side, from 0 to 224, right? That's the semantics of those bytecode. You move to the middle, like NVIDIA case, is exactly double of that value, right? It's 0 to 448, right? So when I say cap, I mean we don't use our code 240. We just use it to up to 2 to 4. We just saccharide one code, right? We use 0 to 2 to 4. And if we use the same, then the meaning on NVIDIA or whatever number they see is just double our value. So that is great. That means if you look at how to do interop, we just need to deal with change the scanning. Right, if NVIDIA's dealing with some API number, they come with scanning factor A. In our case, we just need to modify A to 2A or half of A, depending on how you define scanning factor. And we use the bytecode as it is. Okay, at the bottom here, I drew a little bit of block diagram to just depict the concept. And let's walk through this quickly. But incoming tensor X0, it could be input high precision tensor on the high precision domain. So we need to do quantization to fit in this purple first API gene. So what we do here, it is assume this coming everything from before. It is exactly the same as NVIDIA system. We just want to see how to make it work on AMD system does not intervene with semantics. So basically, we do divide by 2. Right? I wrote vertically the label. And I after that, I do clipping at 2 to 4. I don't use the code before above 2 to 4 to 240. I just wait. I don't need it. Right? And then after that, I do change. Again, this divide by 2 and the 2 to 4 clipping is happening on higher precision domain. After that, I do mechanics. Mechanics means just change using conversion instruction from chip to convert to APA. Okay, the same thing on the weights. If weight is high precision, I do the same thing. Then after this divide by 2 to the 4 clipping and the APA conversion, then it's a legal APA number. It will be consumed by the hardware instruction and it will compute the result. But at the end of the result, I need to recover the scanning. I need to multiply by 4. Right? So basically, we have 2 input. All the measurement application today is just 2 input origin by design a circuit. So I would just call it inverse scanning. Then go back to higher precision. By the way, the circuit always compute accumulated result in higher precision because that's the only way you can do. If you accumulate the numbers in low precision, you can never do logic numerically. So all the circuit in design is always a higher precision, AP32 or AP16. That's the only way it works in hardware. So basically, I naturally fit in the Lexner operation nonlinear, nonlinear Lexner higher precision. I'm not talking about the ReLU, forget the ReLU, it's a very special case. So this makes nonlinear operation happy, nonlinear operation finish to the next level after nonlinear. If it is a gene, story repeats as it is. So okay, I think this just explains the serial operation. So basically, in short, we're not translating a number, a bytecode, and then change the bytecode to make the same number on an MD side or vice versa. We keep the bytecode no change. We just want to do a quick, smart kind of trick to make system work at full speed. And this is how we solve this today in MD. And the fact is we can consume any trained model by NVIDIA chip, by whatever chip for bringing, applying this trick to do the inference or just do forwarding pass with no problem. Yeah, okay. I think they might have a lot of questions, but let's move on because like we can come back to this.
Yes, sorry to interrupt. We only have 4 minutes, so please.
Yeah, I could speed up a little bit.
Faster, yeah, and probably pick up a few questions. Yeah.
So here, let's do quick, right? This is just an emerging floating point. It's starting to be in the hardware of our 335. It's coming in a quarter or so, and I believe to be also in Blackwell. And this is just different. You see on the white diagram here, you have a bunch of numbers that share the same scaling factors at the very left side. And this scaling factor is 8 bits. And this table tells everything. And this on table, the second column to the right is the number representing the scaling factor shared by a bunch of numbers. Here it says 32 number. 32 numbers share one scaling factors, right? And this shared scaling factor, it is not a floating number as we see today in APA. It's really the integer. It's just 2 to the power of this integer. It just shift numbers or something. Yeah, let's move to the next page. Yeah. I will leave this presentation because this public one sanitized, can share with the team. Everybody, please, you can have it. Yeah. So here we're talking about a quantizer. Quantizer today started from like probably a year ago. NVIDIA has MO, probably Han, Professor Song, and his people started to do that. And now they relate a TensorRT model optimizer. We followed it as MD quantizer. We supported all the data types, MO date, and also we were supporting MXFP. Let me run quick. Open source has a bunch. For example, Neuromagic, they start to just put one there. After discussing, they know this idea, they just put in writing up code like that. So optimization, I'm saying touch a little bit. So I just want to share 3 bullets. I think the remain we can skip. For the best performance, this is a lesson learned, right? We the better put the quantization to lower precision in prior non-linear operation. Most time non-linear operation before it is element-wise, whatever, right? Activation function, whatever, they're all element-wise. So you put the quantization there, making that kernel to quantize the high precision number to lower precision, then directly can come into your computation kernel. That's one thing. People sometimes they don't do that. End up with worse performance. The second one is people thinking, oh, your gene do low precision computation, so let gene always output a low precision number. Yeah, if you think carefully, that might not be the case. Actually, can be worse because you need to consider in the context of what gene's output is consumed by. Again, it's most time it's consumed by nonlinear function. If you make a gene kernel right at low precision, you have a nightmare because that guy need to upcast, making high precision. A bunch of things happen. So I'm saying you could make a gene kernel right in low precision. We do that only for special cases. For example, QKB projection, because your projection is a linear function, is a gene, right? And you compute, you make output APA, you just write into the global memory, HBN. First of all, save the memory bundle. So next time you read from the KV cache, and then if next operation on KV cache also using the APA, you don't need to worry about this upcast to high precision. So double win. Yeah. Last one is the most interesting one. So basically, we started seeing a lot of new requirement because now you need to deal with matrix. One matrix might need to have multiple scaling factors. That's very interesting because think about it, if your matrix has multiple channel and you want to do channel-based scaling, so each channel will have their scaling factor. And for MXFP or type of like schema you want to do, every block of data have scaling factor, right? So we need to be able to write a kernel for gene computation with consume matrix come with a lot of scaling factors, and how to design in performant way. That's good stuff to consider. Yeah. Next page, please. No, I'm fast. Oh yeah, I think this is summary, and I think let me just touch the second paragraph here. The other one is easy. Second is more related to probably the project. What I'm saying is here, just for scaling factors management and use cases, we see a lot of chaos today in VRM. A lot of lane who did that or whatever. You see that, right? You see they put a scaling factor in checkpoint, and there's no document or open discussing how to update scaling factor. You may need to redo everything. That's pretty time consuming. Particularly if you want to fine tune or recalibrate your data, you just need to touch the scaling factor, and there's no flow defined or communicating in that process. The second of all, the problem it is people keep changing the keys. Before they say, hey, we discussed, agreed, KV scale. Now there's K scale. Now there's a V scale, and maybe in the future there's a Q scale. Keep adding up. It's really making the code maintaining for user feel not straightforward. So here I'm just saying to make a SGLang very user friendly and less error prone. I was just proposing we can discuss. I'm proposing multi-tier. First of all, if nothing happens, just 1-0, and then we read from checkpoint. Even nothing, that's not theoretically ideal cases. If somebody embedded scaling these keys in checkpoint, we just read once, and overloaded the value 1-0. And then we're looking for our own defined scaling factor files. These files hierarchically is same as model file, right? It's hierarchical, but we just scale keys there with nothing else. But we can add, right? Scaling factor related, maybe MXFP. And then we use this as the last line of data to overload all the data at the same key as before. So basically, I'm saying if you lose third one, you're back to the second one. If you have no even third one, second one, you use 1-0. That's just a simple idea for making the design more robust and compatible to different scenarios. Yeah. Okay, let's for the interest of time, let's move to next page. I think probably one more page. Yeah.
Oh, no.
Oh yeah, that's it.
The last one. Yeah.
Okay, cool. Sorry, I don't have like a code to share today. But I believe if we have follow-up session after some development work is done, it's perfect timing to some code share later. I think let's stop at MXP page. I can stress out some number 6 page, some key important interesting stuff here. Do you want to show page 6?
I think time is
open.
almost up now. Maybe we can end. I think it's
Yeah, maybe we can end. Let's take a few questions if you have. Yeah.
Yeah, we can discuss next time.
Okay. Okay.
Yeah, okay. Thanks for everyone for joining. Are there any questions regarding today's 2 topics? If not, we got to stop our meeting, and we will release our meeting records on later, and welcome to join our Slack if you haven't done that. And also thanks for joining. Yeah, hope to see you next time. Okay, thanks.